Good evening, everybody, and welcome to Space Place Canada's 5th event. My name is Kirsten Vanstone, and I'm a director at the Space Place Canada board, and I'm actually a certified space nerd. You can see I've got, wait a minute, Marvin the Martian over my shoulder, and he's hugging the CN Tower, so I'm not sure how much more Space Canada you could get than that. Tonight, you've joined us to talk about the moon. It's been on a few people's lips this week, as we are going to have a partial lunar eclipse, not tonight, but early tomorrow morning. We'll tell you more about that in a minute. What I'd like to do is show you a few slides. So I am going to attempt to share my screen. And here we go. Okay, so tonight's talk is called From Canada to the Moon. And I say talk, but it's actually more of an event. It's a celebration of our closest celestial neighbor. And we're going to have talks about the moon, how to view the eclipse tomorrow morning, if miraculously it's clear wherever you are. And then we're going to actually take a virtual visit to one of Canada's newer observatories, the Trottier Observatory at Simon Fraser University. Apparently it's cloudy out there too, but hopefully we'll get at least a view of the building. And as a special addition to that, we actually have not only a tour guide of the Trottier Observatory, but the architect who actually designed it. But before all of that, we're going to hear from Randy Atwood, who's been a longtime friend of Space Place, and he's going to tell us how to watch that partial lunar eclipse tomorrow morning. But before we get too much farther, I wanted to tell you just a little bit about Space Place and what we are. Space Place is actually a bunch of very enthusiastic space nerds who, and a lot of other people who want to bring a large planetarium, a large iconic planetarium back to Toronto. This slide I'm showing you here is one of the reasons why. Canada, not many of us know, was the third nation in space with that Alouette 1 satellite. And as you can see, the facts and figures below is we have a very large aerospace industry in Toronto with more than 20,000 people working in it and bringing in $1 billion of wages to the region's economy. So aerospace is a big deal in the Toronto area. Many of us don't realize that. We also have a very active astronomical community in Toronto and in Canada. In fact, here are two telescopes, one a little bit older, just north of Toronto, called the David Dunlap Observatory, which was at one time the biggest telescope this side of the Mississippi River. And on the other upper left side, you can see the Chime Observatory. That's actually a really modern telescope. It's a radio telescope that is measuring hydrogen in the universe and making incredible discoveries. In fact, there are so many astronomy departments in Canada that I ran out of fingers and toes when I tried to count them all. So there's a lot of research coming out of this country, but Canadians aren't always the best at telling their own stories. So we think a big planetarium in Toronto would be a perfect place for this to happen. So I also want to tell you why a planetarium. So you could tell stories about space in an exhibit, and that's great. It's a really good thing to do. And we would definitely want to have exhibits around the Space Place Planetarium. But the planetarium itself is a special thing. These are some images from a modern planetarium. It doesn't quite look like that place that you might have sat and watched Laser Floyd many years ago. Those planetariums use star projectors that showed you the view of the night sky, and that's an amazing experience, especially if you live in a city and don't get to see the night sky very often. But modern planetariums use digital projection to not just show you the view from the Earth, so the sky above you, they can actually take you into space. It's almost like they've made the shift from that Ptolemaic view of the world, that's the Earth-centered universe, to the Copernican one, where the Earth is just part of a bigger system. This is actually not just fun, it's actually easier for people who are watching to understand their place in the universe, something that I think some of us lose track of from time to time. So we would like to bring an experience like this to Toronto. There are planetariums around in the GTA. They're great. They're doing really, really good work, but they're smaller. The big planetarium has the ability to really immerse you in space. A planetarium is a perfect gateway to science, technology, engineering, arts, and mathematics, what some call by the acronym STEAM. And even in the city, if you can pick out the Big Dipper or be taken aback by a rising harvest moon, a planetarium can take that natural curiosity and build on it. It will immerse you in space. So you want to dive a little deeper and learn a little more. And even if you're just casually interested, you'll be exposed to science and math. You'll learn about the power of technology. And of course, nothing in a planetarium works without art. So, what are we doing about it? Well, Space Place Canada, you may have heard, we are really enthusiastic about having a planetarium in downtown Toronto. So, we've actually had an architect, the very architect you'll meet this evening, Bill Chomick, give us some designs for what this building could look like. And this one is situated down by the lakefront, but there are other locations that we could be. We don't actually have a spot yet. The main central feature is that big dome in the middle and a very iconic and striking building around it. If you've seen this picture already, I've got a couple more that we haven't released publicly yet. These are of potential views inside this planetarium. So you can see the exhibit halls here, people wandering around and examining different things. You can see art on the walls. Of course, none of this is planned. It's just a rendering of what it might look like. Of course, there's also a cafe and a place to buy gifts. And the dome itself, the big dark ball in the middle, with a little cutaway into what it could be showing you inside. I hope that these pictures inspire you as they've inspired me. I love planetariums. I've worked in them before. I really, really want to get a big planetarium here in Toronto. And I really look forward to a day when this may actually be a reality. If you'd like to help us on our quest, you can visit our website, spaceplacecanada.ca, follow us on Twitter and on Instagram and Facebook. There are lots of opportunities to interact with us. You can sign up for our mailing list. You can send us a donation. And if you really want to get involved, there are opportunities to become members of Space Place Canada. Now, I'd like to tell you a little bit about who's helping us already. We have a suite of sponsors, including MDA, which is one of Canada's sort of biggest aerospace companies, and we're very grateful for their lead sponsorship of our product. Of our campaign. It's not a product yet. One of these days, we hope it will be. All right. So in light of MDA, I'm just going to take a chance to show you a little video that I find very inspiring about the work that they're doing now. Thank you very much for waiting through there. Just want to check that everybody out there in YouTube land can see the comment I just posted. Hi, all, as I got a little bounce back saying that we couldn't see any comments. And I want to make sure that you can interact with us tonight. So if you have any questions, please feel free to type them in the chat there. And I'd appreciate it if some of you could just note whether or not you saw my comment. Hi, all. And tell me where you're from. Thanks, Julie. Wherever you're from, be nice to know. If you're from the Toronto area, if you're from surrounding areas, let us know. Now, I would like to take this chance to welcome my first guest, who, as I said, is somebody who is a longtime supporter of astronomy in the Toronto area and certainly of Space Place. He was a director until quite recently. And he's a real expert on not only the moon and especially the Apollo missions, but also just sky watching. So if you have been paying attention, you'll know that there's a partial lunar eclipse that's coming up. It's actually going to be really not great for those of us who like to sleep at night, because it's going to start here in the eastern part of the country at about 1 o'clock and be at its peak at about 4 in the morning. So it's not ideal for viewing, but there's been a lot of chatter about this on the internet, and I'm pretty sure that Randy will talk about that. And that chatter has to do with the fact that this is a long eclipse. I don't know if any of you have heard about that. It's supposed to be one of the longest eclipses or partial eclipses for a very long time. So I wanted to turn it over to Randy to find out how we should actually view this eclipse. And as I see some of you clocking in, Haley from Vancouver, who said it's cloudy and rainy, I hope everything's okay out there in Vancouver, Haley. I know you've had a rough time with the rain, but we are going to be going out there a little bit later, so hopefully it won't be raining too hard on our friend Matthew. All right, so I'm going to invite Randy Atwood into the stream here. Randy, as if you've seen me do these before, hello, Randy. How you doing?
Hi, Kirsten.
Randy and I have known each other for quite a long time.
Yeah, a long time.
But yeah. I don't really want to get into it, but I was in grade 6 when I first met Randy, and he was teaching a nice class about astronomy, which is one of the things that got me into it.
So a long friendship.
Long friendship. And I really appreciate him coming out tonight to tell us a little bit about this eclipse. Now, Randy, have you heard this chatter about this being the longest partial eclipse since some Henry, King of England?
Yeah, it was early this morning. I was doing a radio interview for a radio station in St. John's, Newfoundland. And the interviewer had done his research, and he asked me point blank, what do you think of this being the longest partial eclipse since Henry VII? And of course, I'm not familiar with Henry VII, but it's a statistic. What's happening tonight is the moon is passing nearly through the central shadow of the Earth, but not 100%. It's only 97% through the central shadow. And if you go back through your statistics, you will find the last time this happened was in 1400 or whenever Henry VII did his thing. And so, for all intents and purposes, when the moon is passing through the shadow of the Earth and we're seeing a total eclipse and it's 97% covered, then it's not much that you can actually observe. And usually the last 3% disappear pretty quickly. But yes, statistically, tonight is a partial eclipse. Only 97% of the moon is going through the central shadow, and we'll talk about that in my presentation. But it is so much like I likened it to a when they say that this afternoon spring will start at 4:13:27.7. And because we know when spring will happen to the fraction of a second. Does it really matter? No, spring's happening today. So
if only spring were happening today.
Oh, don't you wish? And unfortunately, Kirsten, I saw my first total lunar eclipse when I was in high school. And it was 50 years ago this year. And I got up at 2 a.m. because that's when it was supposed to be total. And I peeked out the window and saw it. And that was great. It was amazing to see this amazing red hot moon in the sky. But unfortunately, I did an analysis recently just because I'm kind of geeky that way. And all of the lunar eclipses since then that I've tried to see, I've only seen 30% because the rest have been clouded out. So these are not all that rare. We're going to see another lunar eclipse in North America in May.
And then another in November?
Partially, yes, partially.
Yeah? Okay.
But for some reason, I mean, there was an amazing lunar eclipse in September 2015. Perfect Sunday evening. We had, public outreach programs in Mississauga and Toronto, and everyone was so excited about it. Totally clouded out. So, sometimes with astronomy you can't win, but when it does work, man, it's amazing. And I've always found that lunar eclipses are just such a wonderful thing to enjoy and to sit through. And they always look different because, of course, the darkness of the moon, this reddish moon at totality, is affected by the atmosphere. And there have been in times, like in 1963, there was a volcano, and the total lunar eclipse in December 1963 disappeared. It was totally invisible, and it surprised everybody. And there was one in 1992, a partial eclipse.
I remember that one.
Amazed. It was so dark.
Wasn't that a Pinatubo eclipse?
Yeah, Pinatubo, right. And
the volcanic eruption.
Yeah, so the atmosphere has such an effect, a demonstrable effect on what we see with lunar eclipses. Scientifically, I don't think anymore these things are all that valuable. Although I know some people take videos of the moon during lunar eclipses because sometimes they get little flashes where you can actually see little meteorites. I don't know what a meteorite on the moon is called, but something that hits the moon and leaves a flash. So there are a lot of things you can do with the lunar eclipse, but the main thing is to enjoy them because they are unique, but not all that unique. There've been some talk today about how long it has been since we've had such a long partial eclipse. But these things happen every 2 or 3 years for where we are. I mean, the last lunar eclipse I saw was in January 2019. It was winter. It was clear. It was a nice total lunar eclipse. And generally these things come in 2 to 3 years, but fortunately we're going to see another one in 6 months. And these things do come in 6-month periods. You remember 6 months ago, we were talking about the June 10th solar eclipse.
Yep.
It's so beautiful as we saw it rise over Lake Ontario, partially eclipsed. So eclipses do come regularly. Every 6 months, not necessarily from your backyard, but I know there are several people who have actually already started heading to South America to get onto cruise liners to see a total solar eclipse in Antarctica on December 10th. So,
wow.
Lunar eclipses and
so they're going
eclipses do come in pairs. They just don't necessarily come to your basic, but there are, I will warn everybody, there are people living amongst you on this planet who will do anything they can to see a total solar eclipse. And so there are people who are paying thousands of dollars to get onto cruise liners to go down to Antarctica to see a solar eclipse on December 4th.
Which, of course, would be getting near to summertime in Antarctica, which
yes, it would be like midnight sun type.
Indeed.
Yeah.
Randy, one of our colleagues at Space Place here, Julie, put together some moon trivia, and I've got a slide that I think would be maybe pertinent to your presentation. So if it's okay with you, I'd like to just show that and invite our viewers to weigh in with their answers. So the trivia question is, let me see. The reason eclipses can happen is because the sun and the moon appear to be about the same size in the sky. That's solar eclipses. So how come? Why do they appear the same size in the sky? The geometry is just right. They are each at just the right distance and look the same size, or they are actually the same size. They don't look the same size, or aliens. So I'm inviting everybody just to pick, what do you think? Is the answer why the sun and the moon appear the same size in the sky, A, B, C, or D? How many of you are going to vote aliens?
Well, obviously.
Let's see. All right, we got A. Oh, okay, good. Yeah, so everybody's on A. So yeah, it's a real trick of geometry, isn't it? That we have the sun and the moon. One of them is 400 times bigger than the other, is that right? But it's 400 times farther away. So it cancels each other out, and you get these two things so important to our history and timekeeping. I hope that wasn't part of your presentation, was it, Randy? Did I just scoop you?
Well, I can zip through that. No.
Okay, good. Well, we got a smart crowd here, so it seems like they got that one right anyway.
That's great. No, I'm glad we're doing this because, it is a coincidence, and I've often and this goes to another thing. And if I can spend a few seconds here talking about, we've been talking about a little bit about media today and how they've been handling this eclipse. But essentially, the moon is about the size of an aspirin held at arm's length.
Okay,
It's not very big.
that's pretty hard for people to believe. Let's let that sink in for a second. An aspirin, if any of us remember what that is.
Well, any kind of
what, about 5 millimeters held at arm's length? That's the actual physical size of the moon relative. Okay.
Sometimes I use
apparent size of the moon.
My thumbnail, but that's essentially the size of the moon, what we call the angular size of the moon, and the angular size of the sun as they appear. They're about the same. So the moon is a lot closer, but it's a lot smaller, but the ratio is about the same. But what's interesting is the moon is in an orbit which is not circular, it's elliptical. So sometimes the moon's a little closer to us, sometimes a little farther. So for solar eclipses, sometimes where the moon is farther away and it can't cover the entire the sun, and sometimes a little closer and it does cover the entire sun. So we're that close in being, the same angular size that the elliptical orbit affects us and gives us either a moon that won't cover the entire sun, what we call an annular eclipse, which happened last June 10th, and in 1994 in Toronto, actually.
Yep.
And a total solar eclipse where the moon totally covers the sun, which we will see in April 8th, 2024, going through southern Ontario, and other eclipses like in December 4th in Antarctica. But it's amazing that it is so close, and it's all a coincidence.
It is. There's actually a couple of science fiction stories that I've read where the aliens come to view a solar eclipse because they come to Earth to view a solar eclipse because they can't see it on their home planet. So it's actually this major intergalactic tourist attraction on the Earth. That's science fiction, just so everybody knows. Some good short stories and long form stories about that.
Okay, but again, the aliens, if they come to Earth, they can always go out in space and just put their hand in front of the sun.
Yeah, but that's not as fun as coming down and interacting with Earthlings and pretending. Anyway.
Just saying, these aliens.
Okay. Well, Randy, why don't you launch into your presentation and talk a little bit about how we're going to see this eclipse, and whether or not it's worth getting up at whatever hour one has to get up.
I will do so if I.
Okay, and as Randy is sharing his screen, I will give you another piece of trivia courtesy of Julie. Where does the moon rank among moons in our solar system? Is it A, the largest, B, the 16th largest, C, the 5th largest, or D, the 20th largest? So you got that. Is it the largest, 16th largest, or 5th largest? A, first, biggest, B, 16th, C, 5th, D, 20th. Anybody know? I'm not showing the slide here.
Yeah, I'm working on it.
Well, no, it's okay. Eric says it's the 5th largest. Everybody else is quickly Googling it. Very good. So we have a few people voting for C, 5th largest, a few people voting for B, which was, I can't remember now, 16th largest, D, 20th largest. All right. Well, I think it's fair to say that this one stumped a few of you. It is, in fact, the 5th largest. So those of you who voted letter C, option C, are correct. So it is the 5th largest satellite of its planet in the solar system. Nicely done. There we go. All right. How's that going? You still pulling up your thing? I got more trivia. I'm good.
I'm working on it.
Okay, no problem. Let's see. Here we go. Here's another one. Are we ready, everybody? We've recovered from that hard question. Here's the next one. What was the first spacecraft to land on the far side of the moon? Is it A, Luna 14, B, Chang'e 4, C, LC Cross, D, Chandrayaan 2? So your options there are. In fact, I can probably put it in the chat if I'm good enough. Here we go. Let's see. No, I probably can't. Okay. Here we are. Let's see if I can get that. Here we go. Okay. So you don't get the first spacecraft to land on the far side of the moon. Option 1, A, Luna 14, B, Chang'e 4, C, L cross, D, Chandrayaan 2. There you go. You vote there while Randy finds his presentation.
I don't know why this isn't working.
Oh, well, that's okay. We got lots of trivia. Julie did a good job putting these together. All right, we have vote for A, Luna 4. Vote for, I'm not sure if we're running into the previous question, Chang'e 4. Sorry, Luna 14, Chang'e 4, L cross. All right.
Can you see my presentation at all?
No, I'm not seeing it come in. You have to actually share. If you share your screen, I should be able to put it in myself. Have you tried sharing it?
I am, but it's not giving me.
Strangeness. All right. We're going to go back to the trivia here. The answer is B, Chang'e 4, and it just landed recently. It's the Chinese spacecraft. So nicely done there. As we try to figure out what's going on with Randy's computer.
Good Lord.
It's the way of things. It's the way of things. As he does that, perhaps what I can do is I actually found a really, really neat video that I would like to show you. I'm just going to get it queued up. And this is a video from the Japanese Space Agency. And it is a very cool thing. So here we go. There that goes. I'm going to go and show that. There we are. Okay. There we go. You do feel like you're floating over the moon here. It's pretty incredible. I'm not taking requests, Henry. Sorry. It is a beautiful video, isn't it? All right, I think we have Randy back here. He's got his things, so let's add Randy in, and I'm going to put your screen. There we go. All right, I'm going to remove myself and let you talk about the upcoming eclipse. And just to remind everybody, what we're going to be doing soon is we are going to be heading out west to take a virtual tour of the Trottier Observatory. And we'll be joined by the architect who designed it and also did the renderings for our planetarium, our proposed planetarium. Randy, one thing before we get going, there's a little tab on the bottom of your screen that says stop sharing and hide. Don't hit stop sharing, please hit hide. Excellent. Oh, woo, fun.
Oh my gosh.
It's okay, just hit the presentation slideshow again, I think.
I don't see it.
All right. Here. Just try sharing your screen again. We're vamping until ready. Anything is on the menu tonight. So if you wanted to know, as Randy pulls that back up again, the image there. The video I showed is from JAXA, the Japanese Space Agency. It's available on YouTube. They have a wonderful channel. They have a ton of really amazing videos there. So have a look. They're really, really cool. Has it disappeared again, Randy?
Yep.
Oh, fun.
Hang
Okay.
on.
That's all right.
I'm working it.
That's good. Do we need another moon trivia
I think
while you're getting it? Here we go. That's okay. So my next moon trivia for everybody, I'm posting it in the chat. So we're having some technical difficulties here. That's okay. You're all bearing with me. Thank you very much. Okay, here we go. The question is, why do we only see one side of the moon? Is it A, magic, B, synchronous rotation, one rotation on its axis per orbit so that one side always faces the Earth, C, it doesn't spin on its axis, and D, the cheese to rock ratio is just right. So what do you think? I think we've got Randy back here. I'm going to wait for him to get his screen ready. Oh, I'll pull you up. Cheese. Excellent. Okay. Yeah, a few of you actually knew the answer there. I think cheese is a good one. That was a very inspired answer there, Julie. Very good. Okay. Let's see. Well, we still don't have Randy's screen share. Kind of strange. I don't know, Randy. Maybe you should just talk about it.
I'm reaching that point. I'm sorry about this.
No, that's okay.
It keeps up, but it doesn't want to.
You know, I'm just enjoying the. I'm enjoying the answers to this. Why is the moon
Okay, well,
show one side?
What we're going to end up with. You know, what's interesting is they were talking about how long this partial eclipse is tonight, which is, it goes back to the reign of Henry VII, and it is a long partial eclipse because the moon passes through the umbra but does not actually fall directly in the umbra or the full shadow of the moon or of the Earth. And so they're talking about how it's the longest eclipse since then, and that's true. I mean, but it's what we are going to see tonight, starting at about 2 o'clock, is the moon moving into the shadow of the Earth, and then taking about an hour or a couple hours or so, moving into the shadow, and then by about 4 o'clock, it'll be about 97% in the main shadow. Now, you know, normally we see a total eclipse and the moon is totally in the shadow. This 3% isn't going to be much of a difference, but it is going to be totally in the shadow of the Earth, and that's a great visual right there.
So this is from timeanddate.com. He'll be doing some live streams tonight as well.
Yeah, and it looks like, based on the weather, that we're going to have to depend on some of the live streams because you know, for the most part, November weather in Ontario and for many places across the country isn't great. I think I remember looking for 2 or 3 lunar eclipses in November in my memory, and seeing one in the 90s that was beautifully clear all night. It was just one of those nights which was just fantastic, but the others were just pretty horrible. So unfortunately, a lot of people will have to either look through various holes in the clouds tonight, or as I say, watch on Time Date to get a live feed.
Yeah, so actually, I got a little bit of a list of different viewing live streams. So for those of you who share Randy's enthusiasm for the weather for a November eclipse, one of my friends out in Manitoba, his name is Scott Young. He's got a nice Facebook page called Scott the Skywatcher, and he compiled a list of live streams of the eclipse. So I can find that. And if my screen sharing looks okay, maybe I can get that for us. Let's see here. Here we go. right there. So there's a whole bunch of these, and I can pop these in the chat for you. So I think Astronomy by the Bay, who's out in Nova Scotia, I think he said that they're clouded out. I'm not sure about Edmonton. Is anybody on the line from that part of the world tonight? We're going to have Bill Chomick on at some point, and he's out in Calgary. So here's a list of these different live streams. So if your view is bad here, hopefully it'll be okay in Flagstaff. That's come through really, really badly. I don't know if you can see that okay. Let me know. I can see if I can make that go better tonight. Flagstaff, Arizona, the Lowell Observatory is going to have a live stream. Timeanddate.com is going to have a live stream from Science North, but I don't think Science North is likely to be any better than we are. And there's a European virtual telescope.eu that we'll be trying to put a live stream on as well. So lots of options if you feel like staring at a computer screen and not at the eclipse. Now, it looks like Randy's got his presentation back.
Yeah,
is that right, Randy?
I'm not going to hit that thing at the bottom.
No, don't. Just don't listen to me anymore. Okay, let's get this off and let's get that back on. Right. Here you go.
Yeah.
So all right. Tell us about it.
Who's had technical issues can emphasize with us tonight. All right. So
okay.
Just some graphics as to what's happening tonight. The moon is moving in its orbit into the shadow of the Earth. And, you know, lunar eclipse 101 is moon gets light from sun, Earth blocks light from sun is really what's happening. And the motion of the event tonight is the motion of the moon in its orbit. And it, you know, it moves rather slowly through the shadow of the Earth. It takes a couple hours to do it. So tonight, the phase of the moon that we're talking about is the full moon, and it is at the point when the Earth is in between the moon and the sun, and that's the only way you can have the Earth block out the light from the sun, and the moon essentially get its light blocked out. Many of us are familiar with solar eclipses. We had the great solar eclipse in 2017. We have an amazing solar eclipse coming up in 2024, where the moon does the blocking. But because the moon is smaller than the Earth, the moon only creates a very small shadow on the Earth as it moves in its orbit, only about 150 or 60 kilometers in size. And you've got to be within that shadow to see the actual effects of the eclipse. Lunar eclipses are different. You're seeing the light change on the moon. So if you can see the moon, you can actually see the eclipse. So the moon, we don't get an eclipse every month. The moon, there's a full moon every month. We don't get an eclipse every month because the orbits are tilted a little bit. But what we do get are different types of eclipses. And there are two main shadows of the moon. It's the umbra, the central shadow, where when the moon is in the umbra, it's totally blocked out of sunlight. And the penumbra, when the moon is in the penumbra, it's partially eclipsed. And so we can have three different types of eclipses. Tonight we're having a partial eclipse where the moon is mainly in the umbra, but not totally. The total eclipse of the moon is something we will see next May. We're getting another eclipse just in 6 months, and these things come in 6-month increments. And then we can get a penumbral eclipse where the moon, and sometimes, as we'll see in a minute, the moon misses the shadow altogether, which is why we don't see an eclipse every month. So getting into a little bit of geometry here, the moon's shadow is inclined about 5 degrees to that of the Earth-Moon plane. So if they were all lined up perfectly, then the moon would cross in front of the sun every new moon and cross into the Earth's shadow every full moon. It doesn't do that. It only does that at 2 points of the year where the line of nodes is lined up, where the moon is essentially crossing that line where the Earth, moon, and sun perfectly line up. Only happens twice a year, so we get eclipses every 6 months. We had eclipses in June. We're going to have eclipse tonight and an eclipse in a couple of weeks from now. So every 6 months you get this eclipse. But for the other months, as you can see, there are times when the moon is either below the shadow of the Earth's shadow, or it's above the Earth's shadow, and we just don't get an eclipse. So that's basically why eclipses are rather rare, but not all that rare. They happen every 6 months. For tonight, we see the moon moving slowly into the penumbra at 6 o'clock universal time. Astronomers use universal time just so that we can say, here's the time you can convert for your time zone. 6 o'clock UT is about 1 a.m. Eastern time, 12 o'clock Central time, 11 o'clock Mountain time, etc. So you have to do the conversion. So the eclipse takes place. The main part of the eclipse is at about 7:18 Universal Time, about 2:18 Eastern Time, where the moon begins to move into the shadow of the Earth, and then the mid eclipse is at 9:03, which is just after 4 o'clock Eastern Time, when the moon will be as far into the central shadow of the Earth that we'll see. And then again, it moves off, and it takes a few hours to move out of the shadow into partial eclipse and then penumbral eclipse. I kind of like this diagram from Fred Espenak because it shows not only the moon's passage through the umbra, but it also shows who on the Earth will see the eclipse. And this gives you a really good indication of who will see the eclipse tonight. If you're in the lighted area here, you will see all of the different phases of the eclipse. In fact, this points out where the moon will be directly overhead at maximum eclipse. And of course, our friends in Hawaii are perfectly positioned for that. Here we are in Southern Ontario, where we're coming to you from tonight. We will see the entire eclipse. And essentially, if you can see the moon tonight, you can see the eclipse. It's not like a solar eclipse. If you can see it, you can see the shadow falling on the moon. The moon is visible from half of the Earth at any point in time. So at least 50% of the land mass on the Earth will see the eclipse tonight. But because the Earth is rotating, you have several areas that will see the moon actually set during the various phases of the eclipse, and various phases rising for the people here during the eclipse. So Australia will see a large part of the eclipse. South America will see a large part of the eclipse. Africa will see some of it. Europe will see some of it. Africa will see a small part of it. But it looks like North America and the Pacific Ocean are in good shape for tonight. So, here we are just after 9 o'clock. So we're just a few hours away from the beginning of the eclipse. 2:18 is when the partial phases begin, and 4 o'clock, just a little over 7 hours from now, is when we will see maximum eclipse. And for most people, the penumbral or the eclipse will end just before sunrise. So what do we expect to see? Well, during a lunar eclipse, you see various aspects of the moon moving into the shadow, but also because the shadow is affected by the Earth's atmosphere, you see different brightnesses during the total phase, and you see this mysterious red color of the moon during the central eclipse phase that we'll talk about. But it changes from eclipse to eclipse, which really impresses me. I've never seen one eclipse that I can compare to another, and I've seen several over my experiences as an amateur astronomer. So right about now, if you're on the moon looking towards the sun, you see the moon the Earth approaching the sun from the right. So right now we're on the moon moving towards the right in our orbit, such that the Earth will eclipse the sun. And right now, if in the sky, if you have clear skies, you go out right now, you'll see a beautiful full moon, just a few hours away from eclipse. As the Earth begins to cover the sun, we get what we call penumbral shading, and that is essentially areas on the moon will begin to see parts of the sun covered by the Earth. It's not all that obvious from our point of view. We can begin to see dark shading as the penumbral eclipse continues, but it's not all that obvious. Once the Earth covers the sun completely, then on the moon, you get what we call umbral shading or partial shading, and you definitely see a darkness. And this is what we call the partial eclipse, which will start just after 2 o'clock Eastern time. So it takes a little while for the moon to slowly move into the shadow of the Earth. It takes about an hour for the moon to move in its orbit about 1 moon diameter. And so here we see the moon slowly moving into the shadow, of the umbral shadow of the moon. These pictures were taken from an eclipse in 2010, which was a wonderful December 2010, nicely clear, that I viewed from my driveway in Mississauga, believe it or not. And the interesting thing is this picture here, about 12 minutes before totality, or about a few minutes before what we'll see maximum eclipse tonight. This is a rather short exposure to show the penumbrally eclipsed moon, but a longer exposure begins to show interesting colors in the umbral shadow of the Earth. Not only do you see some reddish colors in the bottom, but you actually see some bluish colors in the top, which is rather interesting. So as the moon moves into the shadow of the umbra, it is pretty obvious that we begin to see some reddish colors. And this is a photograph that I took during that eclipse in 2010 from an urban site, so it was kind of cool to see all the stars. But it was a rather bright eclipse with a lot of reddish color. And the reddish color is due to the fact that the Earth has an atmosphere. And what we see is the light coming in from the sunlight from all of the sunrises and sunsets of the Earth being refracted inward towards the shadow of the Earth and falling on the moon. So the interesting thing is that depending on what's going on in the atmosphere around that terminator or the sunrise sunset point of the Earth will affect the brightness of the eclipse. And remember, we talked about volcanoes affecting, sending up amazing amounts of ash into the upper atmosphere. That can affect the brightness of a lunar eclipse. We expect a moderately bright eclipse tonight. There's nothing to prevent that. If you were standing on the moon, I really like this. Don Davis is an amazing artist, and he just published this recently, a depiction of what you would see if you were standing on the moon tonight during the eclipse, during total eclipse, or at least where you're totally in umbral eclipse. You would see the black Earth surrounded by a red arc of sunlight, and then you would see the outer parts of the solar corona. Very cool artist depiction there.
Hey, Randy.
Yeah.
I'm just coming in to jump in to say Don Davis is a planetarium artist.
Ah, there you go. And he's a good one.
There you go. He's a good one.
He's been doing it for a long, long time.
Yeah.
So during the eclipse, as I say, there is actually a way that you can measure the brightness of an eclipse, this Danjon scale. And L0 is a very dark eclipse. You can't see the eclipse at all. That was 1963. All the way up to L4, where you can see a very bright copper red. And my first eclipse I saw in 1971, I got up in the middle of the night just to look out and see it. And it was like a red hot penny sitting in the sky. So I will never forget that view. And I think that's what turned me on to lunar eclipses. So after all the excitement, the moon will take another hour or so to move out of the shadow of the moon, of the Earth, and the eclipse will end. Now, there was an eclipse similar to this one in 1997, not a 97% eclipse, but a 91 or 92% eclipse. And here's a picture of that one. This one, the northern part of the moon was just barely out of the umbra. So that's kind of what it looked like. So tonight it's the southern part that is just barely out of the umbra. The amazing thing about this eclipse was that the amazing comet Hale-Bopp was in the sky. And I remember turning around and taking this picture of Hale-Bopp near the constellation of Cassiopeia. So here was this near total lunar eclipse, and this one of the brightest comets of the century, Hale-Bopp. So it was a really amazing night. If you have clear skies tonight and you want to take a picture, let me give you a quick little bit of advice. You need a telescope. If you don't have a telescope handy, you need a long telephoto lens. But the amazing thing is during the eclipse, the brightness of the moon changes from a point where you're going to need 1/500th of a second for the uneclipsed moon down to several seconds for the moon in the umbra where you want to capture the red color. So fortunately with digital cameras, we can take as many pictures as we want and see the results right away. So I would go out and take as many pictures as you can. And I wish everyone clear skies and good luck, and enjoy this eclipse, which is apparently the longest partial eclipse for
ever
700 years. And you got to wait another 5,000 years for another one. I don't know. It's
no, it's
hope
something
everyone enjoys it. At
a
least
little bit crazy.
you see something. Yeah.
I don't know. I've got a little note on my weather app that says snow starts in the next hour. So I don't know if I'll be getting up. It's hard to say.
Well, let me tell you one more eclipse story, then I'll let you get back to your program. But there was an eclipse in September 1979, and it was one of those middle of the night ones. And by about 10 o'clock, it was perfectly clear. And I went, okay, I'm going to bed. I'm getting up at 3 in the morning. And it was, I got up at 3 in the morning, totally overcast, just socked in. And I went, oh, darn. And I went back to bed and got up at 8 in the morning, totally clear. So this is the kind of thing we deal with as amateur astronomers.
Yeah, I call the forecast that is partly cloudy the astronomer's forecast.
Yeah.
You can do nothing with it. Absolutely nothing. Anybody who's watching this, if you have any questions for Randy, we can leave him here on the screen. Our next guest has actually come into the studio as well. So I'm going to pop him up on the screen and see if he's ever seen an eclipse. So I'd like to introduce to you all Bill Chomick. Hi, Bill.
Hello.
Just pop you up there. Hello. How are you? Are you out in Calgary right now?
I'm in Calgary and the skies are clear. So
nice.
All right. So we had Tell Us World of Science Edmonton, their live stream. I did put it in the chat. I'll put it in again. Probably worth looking up then, eh? Do you think Edmonton's clear?
I don't know. Hopefully not. I mean, hopefully. The Edmonton Calgary rivalry race.
No rivalry out there. Yeah, I wouldn't want to presume that you're just all doing the same thing. So,
yes.
Bill, have you ever seen a lunar eclipse?
Well, I think what I saw was a solar eclipse, actually.
Okay.
Where
quite different.
I drove. Yeah, they're quite different. Yeah, I probably have over the years. Yes,
okay.
I have.
Yeah.
And it's an amazing time. You know what happens to your body when you see one of those things is you just like start to shake and go, oh my God, this is so amazing.
The solar eclipse. So for those of us on the eastern part of the country, 2024 is a total solar eclipse, and it's going to be mayhem and pandemonium, I think. But it's in April, so the astronomer's forecast will no doubt be in force for us. But that one's going to be visible over quite a large swath of the country, is it not? Randy, you're the expert. 2024?
Well, it's going to be visible from Western Canada. It's going to be a partial eclipse. It may not be all that exciting. But for everyone through Southern Ontario, Quebec, New Brunswick, PEI and Newfoundland, it's going to be an amazing show.
Excellent. We actually have a question, Randy, from Henry. Do you know why some people believe the moon is hollow?
No.
I don't know if Eric Briggs is on this, but he may have something to say about that.
There's actually no evidence that the moon is hollow, so
None at all. No, actually, here's a question. So, Bill, you weren't here earlier. We've had a little bit of lunar trivia. So, Julie Tomei, one of our colleagues here, put some lunar trivia together, and I'd actually like to just see if you have any idea what the answer to this is. This is for everybody who's watching as well. The next question on our lunar trivia is the color of the moon. Is it A, about the same as that of asphalt, maybe slightly worn asphalt, similar to that of blue cheese, light gray, or metallic, as in that's no moon for you Star Wars fans? So what do you think?
Oh boy.
If you're watching, you can vote A, B, C, or D.
I'm thinking probably light gray.
Light gray?
Yeah, that would be my choice.
That would be your choice?
You know what?
Okay.
I design planetariums. I design observatories, but I know absolutely nothing
about the content. Fair enough. Fair enough. So
well, the answer is A, of course.
It may surprise you to know it is about the same as worn asphalt.
And it's interesting that most asteroids that they visit are essentially as dark as asphalt. They just, and even some of the outer moons of the solar system, they just don't reflect much light at all.
Yeah, it's quite amazing. So, yep, everybody who voted C, Pride, and Nelly, awesome, good job.
Although blue cheese is an interesting selection apart from just cheese in general. I mean, I would have selected brie or
maybe that stuff that's covered in ash.
There you go.
Seen that? Yeah, they age the cheese in ash. I can't believe we're talking about this. Okay, thank you very much, Randy. Any other questions that come in for Randy? If he's going to be leaving the stream now for now. But we can pass them along. I can try to answer them as well, or you want to hang out in the, you can hang out in the studio. And if you have questions,
I'll hang out in the dungeon where you sent.
Awesome. Okay, I'm sending you into the void. Bye, Randy. Thanks very much. All right, Bill, thanks so much for joining us. Tonight, I actually did show a few of the pictures that you put together of a potential Space Place planetarium. We did show those, so they're just beautiful, just a wonderful thing to think about Toronto actually getting a design of yours. How many planetariums have you actually designed? I had that somewhere. It was a lot.
Actually, I had to do a tally the other day because somebody else asked me that question. I've designed 30.
30?
Yeah.
Wow, and not one here.
Not one. Well, no.
Not one that's been built anyway. Yeah.
But I've designed 30 planetariums around the world, of which about 18 have been built. So you have to understand that quite often you design a building and they can't get the funding to build it. So it just sits in abeyance for a number of years.
Right.
Or forever, whatever.
Yeah.
But 18 have been built and 30 I have designed. So
wow, amazing. And that's a really impressive actually number. I don't think there would be anybody else around who's designed that many, would you say?
No, I don't think so.
So we get you in the world record?
Yeah, I think so.
Well, tonight we're going to visit one of your other creations, which is the Trottier Observatory. And I see that Matthew Simone has joined us. Yep. I can pop him in so we can maybe see a little bit of your building. All right, Matthew, if you can hear me, I'm going to put you up in the broadcast now. So here you are, Matthew Simone. Welcome.
Hello. Thank you.
How's the weather out there?
It's raining. As you can imagine. It is. It's raining and it's a bit chilly, but our passion and love of science will keep us warm, and it's going to be great.
Wonderful. Well, Bill Chommick's here, who designed the building that you're standing near, and I was hoping could tell us a little bit about it while you're there. We can see you. We can see some lights in the background, but where are you right now?
Yeah, so we're on Burnaby Mountain at Simon Fraser University, which is where the Trottier Observatory is located. And Bill, I'm actually excited that you're here because I've never met you before. And I've worked here for 6 years now, and I've never had this opportunity. So I was excited that you were in the chat feed or in the stream too. So now we get to hang out together. So that's great.
This is what Space Place does. It brings people together.
Yeah.
The last time I was there was the official opening. I haven't been back. No, I've been back to Vancouver a few times, And sorry, I should come and see it again.
Yeah,
But
please do.
no, I was there for the official opening, and I haven't been back, but I will make a trip back for sure.
Awesome. So yeah, what I was thinking I could do, there's a couple cool features on the outside, what we call the science park at the observatory. So I thought I'd show off some of that stuff, and Bill, feel free to riff off anything that I'm showing at that point. And then I'll bring us inside so we can actually look at the technology that makes the observatory work. And then I figured I could actually show some of the stuff that we've accomplished with the telescope. I was hoping that we'd be able to see through it today, but unfortunately, that won't be possible. It's why we have space telescopes, because then we don't have to worry about the weather here on the West Coast or in other parts of the world.
This is true. And there's another space telescope going up in a few weeks, isn't there?
That's right. In December, James Webb Space Telescope.
It's been a long time. I worked in a planetarium when I first heard about that one.
It's even a little bit more powerful than our telescope. Just a little bit.
Oh, just a little. Okay.
Just a wee bit.
All right. So why don't you show us the science park, and then maybe Bill can tell us a little bit about the inspiration behind it.
Yeah, I was going to see now. I don't know if on the fly I can switch directions that my camera is looking in this mode, so I might have to just flip back and forth. So hopefully everyone can see kind of what I'm looking at in this direction. But over here, there's a bunch of kind of glowing bollards, and I hope you can kind of see off in those directions where they are. They kind of lead over to where the rest of the facility is, which is over in that direction. The reason why I started with the bollards is that as they glow, if you could actually see them from the sky, the idea is that they kind of spiral in, kind of like the arm of a spiral galaxy. The only time I've actually seen them from above to show how that works is when we saw some drone footage that someone took, which they weren't supposed to do, by the way, but thankfully they posted it on YouTube. So we were able to see the facility from the air, so you could actually see what it looks like. And then as you get closer, each one of these bollards that they're glowing here will lead you over toward the dome, which is over in that direction. We'll see it a bit better when we get closer. And towards this plinth that we see here, which is basically a whole chain of 6 different elements that we see all the way down the end. Basically our emission spectrum of all these different elements. So we picked 6 in total.
Wow.
And I'll go along each and show them along the way. We also passed just over here. I'll show quickly. We have this is our sundial that we had that was built in combination with BCIT here as well. So we have a sundial that's kind of on the outside too.
BCIT for us East Coasters, what does that mean?
It's a British Columbia Institute of Technology.
Gotcha. Okay.
So we built it in concert with them. Part of the idea was, and Bill, you can probably build on this as well, but we wanted to have sort of like I would say retro and historical theme to some of the astronomical elements that were here. So that's why we have the sundial, and later on toward the end of the plinth here, we'll see that we have star charts set up, and they're kind of set to mimic those monolithic, like rock-like structures that were built by ancient civilizations to track the motion of the stars and planets.
So
that's right.
Bill, that was an inspiration? Yeah?
Well, the science park, the science park actually is PWL, who were the landscape architects. They were just awesome to work with. What they did is they looked at the power of 10, they looked at history, they looked at the future, and they imbued this park with all kinds of different cosmological experiences. And our building was kind of there. It was set aside from the park, but the park was an experience that could be experienced in the daytime and in the nighttime. And I know you can see all the interesting lights going on, but they have about, I would think, half a dozen, 6 to 7 things going on all at once in that park to really talk about cosmology. My role in this whole thing was to design the observatory and the spaces around it. And PWL did the science park, and the two of them are working together like this. But let's put it this way. They did a spectacular job of interpreting all kinds of cosmological issues or a story around cosmology and putting that together in a park, which is abstract to people that don't understand astronomy, but it's pretty clear to people who do.
Okay, so that's it's incredible. I've just, of course, figured out how to make Matthew's feed a little bit bigger so we can actually see what's going on, which is what I was trying to do there. I just wanted to point out for those of you who may not be so astronomically inclined that there's also a really clever trick here. Things are well illuminated, but they're illuminated in such a way that your night vision is still preserved.
Correct.
I think I would like to say that was probably deliberate. I hope so.
Yes.
Because yeah, if you get exposed to bright light after you've been out in the dark, then you just can't see so well. We got a lovely view of the terrible weather as well, which I know Vancouver is famous for. So
It's true. Yeah, that is true.
So that's the emission spectrum?
This is the emission spectrum, a spectrum of 6 different elements, and it runs the whole length of the outside of the science park. And so for those of you who don't know, an emission spectrum, when each element in space, if it's exposed to energy, once it re-emits that energy, it does so with a certain fingerprint of light. And when we look at that light from space, it helps us to determine what a distant object is actually made of. So for example, the one that we're sitting beside right here, with the colors with the red, and then we've got some of the indigo and then the purple. These are colors that are emitted by hydrogen, specifically over here, mainly in the red, which we call hydrogen alpha. And if you get close enough here, you can actually see that there is the H for hydrogen. I think you can make out there a little bit on the edge of the plinth. So that's the first of the element stamps. And each of them was selected for a certain purpose. So hydrogen, mainly because hydrogen is the most abundant element in the entire universe. It was Cecilia Payne-Gaposchkin, who was an astronomer back in the early 1920s, who discovered that stars were made of hydrogen, and therefore, since they are the most glowing-y things in the universe, then most of the universe is indeed made of hydrogen. The next one that we picked over here is helium. Helium is the second most abundant element in the universe, and so it was the second on the plinth. And as we're walking along, on the other side, I'll show here on the ground as well, we have prints on the ground. They're called the powers of 10 print. So as you're walking along, we're actually changing different sizes of objects to show you that as you're proceeding, we're going from, this one is 10 to the negative 8 meters, and it's the size of the ATP enzyme, which helps to do basically biology inside of your body. Next one we've got, like over here, for example, is 10 to the negative 7 meters, which is the size of the HIV virus. Then you go over here, you have like 10 to the negative 6 meters, which is the human size of the human chromosomes. Each one of these things is getting 10 times larger in size. I won't do every one of them along the way through, but as we're walking, we'll see that we'll basically get from, subatomic and then to molecule size all the way to, at the end, we could basically get to the size of the known universe just in, 50 or so steps, which is pretty cool. So let's see. So we got helium that we just passed over there. Next up, we've got, on this side, we've got carbon. And carbon was selected because carbon molecules are what help us to, or carbon atoms are what help us to form our molecules for life. So when we say that life here on Earth is carbon-based, that's because carbon is in our molecules. It helps to kind of put us together. And whether it's DNA, the cells in your body, plant life, animal life, it all requires carbon in order for it to all be stuck together. So that was one of the other reasons that we picked carbon. So hydrogen, because it's the most abundant element in the universe, it's the glowing of stars. Helium, because it's the second most abundant. Carbon, because it's necessary for life on our planet and life as we know it. Later on, we get over here to aluminum. And we have aluminum on here because it's the most abundant element in the crust of our planet. And then we keep going over here until we get to, we have a gap here in our space. And along the way, we're going to get to this bench that we have outside, which is new. It is our new moon bench. And it actually shows the phases of the moon. So there's a lot of students that are often sitting out here and hanging out. There's a great quote that's on the bench, and it's from Apollo astronaut Bill Anders, and it might be shining too much light on here, but it says, we came all this way to explore the moon, and the most important thing is that we discovered the Earth. And it's actually one of my most favorite quotes from the Apollo missions, because in fact, I think, if I'm right, the most often printed photo from the Apollo missions is actually Earthrise. Which is an image of not even of the moon, it's actually of the Earth. Bill Anders was one of the people who took the photo on Apollo 8 of the Earth, and it was the most distant photo of the planet ever taken by humans at that time ever. And I like to think that that's true of the inspiration that we get here at the observatory as well, is that when we're looking out into space, it's also ultimately a way for us to look back on ourselves and our own planet and understand ourselves better as well. Okay, moving on. Can we get to the cool finale at the end of the plinth
Oh,
here?
we got a finale coming up.
Oh yeah,
Right.
so
Wow.
we have
All right, here we go.
we have silicone, first of all. I believe we chose it because of the silicone is required in the computer revolution, without which we wouldn't be able to do a lot of the astronomy that we do now. And finally, we have sulfur, which is at the very end of the bench. And that leads us into this cool, dramatic kind of end of the plinth, which is where our star charts are floating here. There's a lot of pictures you can find online on Instagram tagged with the Trottier Observatory with these. Bill, did you want to talk about this kind of this end part of the plinth here and the design of the star chart area?
Sure. I mean, the end of the plinth actually was a precursor, if you will, to going into the observatory.
Yes, we can actually look at it from the other direction.
You know, it's representing the cosmos in different seasons, different times, different situations, but it becomes more educational as you move in, and then as you move through, then you come into the observatory and you actually get to experience the real thing. So that's what that's about. Personally, I tried to understand what they were doing, and I appreciated what they were doing. But to be honest with you, it was the building that I was really focused on in this whole experience. But I do know that they wanted it to be to gain intensity as you went through it, and then when you went into the building, it was like the big thing, right?
Yeah, big thing. So yeah, again, some of the inspiration for, like, especially you've got these the large kind of monolithic blocks on either side, and it wanted to be reminiscent of some of the structures like Stonehenge, other civilizations that they used to try to monitor the motion of stars and planets. And so over here we have, these are my favorite part of the outside of the planetarium, is the glowing star charts. So we have these incredible star charts that are here on the wall that are illuminated at nighttime. Each one of them, it tells you what time of the year that you'd be able to see those stars in that particular part of the sky. So for example, this is winter facing south. And it'll show you the magnitudes of each of the stars that you're looking at. So whether it's a magnitude -1, which is the brightest star in our sky, which is Sirius, and then magnitudes, each one of them, when they drop, you're looking at a 10 times drop in the brightness of that particular star when we're seeing it from Earth. And then we've got a legend of some deep sky objects, so galaxies, globular clusters, open clusters, nebula, that kind of thing. So they're all here on the star chart, along with the constellations in that part of the sky. And I get a cool piece of Trottier Observatory trivia that you might probably not know about. But if you come by one of these charts, and this is on the winter facing south, there is only one star that is magnitude -1, which is the brightest one in our sky, and that's Sirius, which is the dog star. It's supposed to be a companion star to Orion the Hunter. So Orion is here. You can see the 3 stars of Orion's belt. There's Betelgeuse, which is his left shoulder, right shoulder. And Sirius is this star right here. And when we first hung the plaque up, we were all looking at it and noticed that the brightest star in the sky was actually missing. It wasn't on the plate. And so we had to go and drill Sirius in afterwards because it was actually missing from the star chart. So we realized there was a little bit of an error there, but we fixed it, and now it's okay. And then over here we've got
nothing a drill can't fix.
That's right. We have fall facing north. Over here we have summer facing south, and then spring facing north. And so it'll change throughout the course of the year. So you can basically, the best way to think of this is with one of these circles, because down here you have the southern horizon at the bottom, the northern horizon at the top. So this is the sky directly above you, is at the center. We call that the zenith. And you can imagine as if this were the circle of the entire sky from horizon to horizon, all the way around you. And they're beautiful. I love them. And like I said, there's a lot of photos you can find from students all over campus who have found this at the middle of night and posted it on Instagram, which is super cool. And then, of course, finally, we get to the main actual observatory building, that big iconic dome that you find on the campus. And we have one really cool new thing that we added. This is recent. So a new addition to the outside of the observatory. I set up a light here so we could see it properly. And this is the cosmic calendar. So we have a calendar on the outside of the observatory. It's a mosaic, so it's made of these tiny little pieces. And the calendar represents a timeline of all of the history of the universe as set out in 365 days. It was popularized by Carl Sagan, and it was used in his series Cosmos, and then it was reused again in the reboot Cosmos series with Neil deGrasse Tyson. And we actually got permission from the series to be able to recreate it on the outside wall of the planetarium, which is awesome. So each one of the days in cosmic time on the cosmic calendar represents about 38 million years in cosmic history, which means that every second is about 400 and some odd years, which means that the Big Bang is here at the very beginning. So it's represented by this explosion outward in January. The galaxies first start to form at the end of January, beginning of February. So this is the formation of the earliest parts of the galaxies. March, we have this spiral here because this is when the Milky Way started to form its disk. So our Milky Way dates back to about March in our year. And our solar system doesn't start forming until about August. So that's when our sun forms here at around August. So midway through the year. And if we skip all the way to December, so this is current day, and there's kind of like a map here of the green sort of coloring is supposed to be of the Earth. So this is the time of us on our planet. And we would have shown up, humanity, on the last day, and we've only been around for about 7 minutes on the last day of December the 31st. So kind of gives you an idea of the short amount of time that we have spent as part of the universe's history so far.
It's perspective. I was talking about that at the beginning when we talk about the new planetarium style, where you are not looking at an Earth-centered universe. You're actually immersed in the entire universe, and you could shift your perspective. So it's quite amazing. So, Bill, that's an addition to your building, but we're now at your building. So what was your brief when you were given given the go-ahead to build this? What were you asked to build?
Well, first of all, the mosaic on the outside of the building was always a placeholder. When we first designed the building, we didn't know what Simon Fraser was going to do with that space, but we knew it was going to be a mosaic tile. So when we applied for the development permit and the building permit, we said this would be a mosaic tile expression of some sort, and clearly they've done
gorgeous. It's a nice expression.
Wonderful job.
Yeah.
But from an architectural perspective, our key driver here was that the Simon Fraser said to us, can we do something that's absolutely barrier free? In other words, when you go into most observatories around the world, there's all kinds of ramps and stairs and
ladders
and this, that, and the other. Can you create something which is just flat? So that was the biggest challenge that I faced as the architect on this building. And I thought to myself, well, I'm not sure what to do, but I went to Los Angeles. I want to go to Las Vegas. I went to Los Angeles and I met with the plane wave people there because they were going to buy a plane wave telescope come hell or high water. And I met with them and they said to me, you're going to have these ramps and these stairs to get to the eyepiece of the telescope. And I said, because there's something we can do to avoid all of those stairs, those ramps, all of that stuff, all that paraphernalia that normally comes with the base of an observatory. And they said, well, we're not sure. So we talked about them developing an eyepiece or a telescopic piece that would bring, without losing any clarity whatsoever, bring something down to street level, which is what we call it, street level, so that somebody in a wheelchair, a child, or an adult that's completely healthy, if you will, can look into this eyepiece and see with absolute acuity everything that you would see if you were in that normal eyepiece way up there. And I convinced Simon Fraser University to spend the money on this eyepiece instead of on all these ramps and stairs. So there was, let's put it simply, there was a budget of about $100,000 for ramps and stairs. And I said, let's take that money, let's give it to Planewave, and let's see if they can develop a telescopic eyepiece that brings everybody down to the same level, and so that everybody can see it, right? And
they went for it.
They did. They went for it, and about, I don't know, a month later, they came back and said, "We think we can do this." So the Simon Fraser University, great client, said, "Let's do it." So they did. They put this telescopic kind of eyepiece onto the normal eyepiece up there, and guess what? We have the first totally barrier-free, stair-free, ramp-free, encumbrance-free observatory in North America.
Wow.
And we should go look at it.
Can we?
Sure, let's do it.
All right. That's really interesting, Bill. I did not understand that. I mean, I've heard a bit about this observatory. I've seen the external part, but that is a remarkable accomplishment. So now, was it meant for it's meant for training and outreach, or is there research done here too? Matthew may know that.
I think it's sorry.
Go ahead, Bill.
Both.
Okay. Yeah.
The observatory was designed for 30 students, which is a classroom, right?
Okay.
32. So the observatory is designed to have 30 students standing and being taught. But we were able to do, it's a 20-foot diameter building, so it's about 380 square feet, 350 square feet, whatever it is, where a bunch of students can stand, and they're just not encumbered by the usual stairs and ramps that you get in a planetarium or in an
observatory.
Yeah, sorry.
That's okay. They're both round and have domes.
Yeah, that's right.
We get them mixed up.
That's right. So yeah, there's an eyepiece that comes down that Planewave designed, which is really pretty cool.
Yeah, can we see that?
There
Matthew,
it is.
You've got it?
Yeah.
Wow.
So this, normally the eyepiece would be up here. So normally you'd have to climb up on like a ladder to get up to where the eyepiece was.
Right.
But this is the periscope that was created so that the eyepiece comes all the way down to a seated position. And because our telescope is a fork mount rather than what's commonly known as like an equatorial mount, the eyepiece doesn't come out of the back of the telescope. So the eyepiece is never going up and down. It's only ever moving circular left and right around the telescope. So it's always at the same level. So you can always be in a seated position. There's no stairs, no ramps, anything. You can just come straight in, literally sit in front of the eyepiece, no matter where it is around the telescope, and then head back out. And I'm glad Bill brought this up, because it's actually one of the things I'm proudest of with our telescope, is that it is so easily accessible. And I remember this was a conversation that came up in one of the early designs when we weren't sure whether or not we would be able to have the periscope be constructed, that we weren't sure whether it was going to work. And I remember the decision was one or two things. We could either leave the telescope up where it is, or we could lower the whole thing down so it's not on such a high pedestal, so that it was still at an accessible level. But when you do that, because you've got the dome opens way up here, so when you bring the telescope down to a lower level, that means you cut off a large portion of the horizon of what the telescope could see. And I remember that even then, the design choice was we'd rather cut off things on the horizon and have everyone be able to come in and see what's left than to have the telescope at an inaccessible height. And thankfully, we didn't have to make that decision because the periscope was constructed. And so we have that more accessible version. So it ended up being the best of both worlds that way, which is pretty cool.
Exactly.
Very interesting. So if you get a class in there, let's say you got 30 students or something in there, I mean, that's pretty remarkable. I remember being in a dome when I was a student, and if you had 10 people in there, you were kind of stepping on each other along with all the equipment and stuff. So that's pretty remarkable. Were there any other special requests when you were building it, Bill? Any
Well,
other,
one of the
the
things we
location,
wanted
the site, yeah.
yeah, quite a few special requests. First of all, when we positioned the observatory, it was really important to be able to find a place that was doing two things. One, wasn't impeding the visual aspects west, east, and south. North wasn't such a big deal. Secondly, they did not want to have a whole bunch of students on a daily basis coming through the site. They wanted to make sure that there was some kind of quietness about the site. So we were very careful about where we located the planetarium. The second thing is that they wanted to make sure that when people were dropped off on the mall, which is what it's called, that they could come with a wheelchair, or they could come with some sort of, whether they were in walkers or whatever the case may be, because a lot of older people do come here. They had not a single step to negotiate to get into the observatory. So that was another really critical part of that whole science park design. Thirdly, we wanted to make sure that the Ash Dome, which we had, Ash is a company out of Chicago that makes these domes with the shutters and so forth. We wanted to make sure that the facility worked really, really well to the east, to the south, and to the west. And finally, on an architectural scale, we wanted to make sure that whatever we did kind of paid homage to Arthur Erickson's beautiful, beautiful historic building, which, the quad and all the other buildings that were around it, which were made of precast concrete, or cast and place concrete and precast, combination of the two. But for the most part, we didn't want to challenge the architectural expression of what was already there. So that's why we made this building out of concrete. We made it very quiet. We did not try and challenge what was there. We did not try and make an architectural expression which was exuberant. We simply said, we think it's really important to respect Erickson's original design, and kept it really, really quiet. That's why the building that you see, the park is a little more exuberant, right? It's got lights and stuff going on in it, but the building is very quiet. So these were a lot of the architectural considerations that we had when we were designing this building. The other thing is hey, this is Vancouver. There's earthquakes.
Yeah, I was going to ask about that. Yeah.
So we had to make sure that the pier, which is the base that the plane wave telescope is sitting on, we had to make sure that that pier was extremely solid and isolated from any kind of significant movement. And you can't see it, but that pier is not touching the floor.
No?
That pier is shooting through.
Okay, going down. Yeah.
Many, many feet onto solid rock. And it's just a rubber gasket around it, so that if there is an earthquake, or actually, it's not even about an earthquake, it's about movement. The earth moves all the time, and it moves a little more in Vancouver and the lower mainland than it does in other parts of the world. So we had to make sure that that telescope was isolated from that movement as much as possible. So when you're looking into the eyepiece, things aren't doing this, right?
Right.
It's a nice solid.
Yeah. So a good solid mount in an earthquake zone.
Exactly.
It's amazing.
Yeah, and that was, yeah.
I just want to mention this because I've read a little bit about the construction of early mountaintop observatories and all the difficulty that they had. I mean, you're not too high up there, I suppose, but did that pose any of a challenge with the design?
Not really. Actually, it was an advantage because we were closer to the stars than you would be if you were on a.
Well, that's why they put them up there. That's right.
Right.
It's in the early days, it could have been quite a thing to try and do that. All right. Well, Matthew, is there anything else you want to show us up there?
So, I
think your feed's breaking up a little bit, Matthew.
Oh, let's see.
That's better.
I might because I'm inside. Okay, I'm better.
Yeah.
All right. Yeah. So part of it is when we have our telescope tracking throughout the night, it has to remain as steady as possible. It's actually tracking right now. The telescope is fixed at one point in the sky and it's slowly moving. And we actually have a tracking quality indicator. So this is the software that runs our telescope. And as Bill was mentioning, it's from a company called PWI or Planewave. This is the Planewave interface, so the software that actually runs it. And this is the motion of the telescope. And we're talking over a very, very fine, minute amount. In the circumference of where the telescope rotates, there are actually 16 million position sensors. So 360 degrees divided by 16 million different individual sensors that shows where the telescope is pointing. So watching this tracking sensor, I'm going to take a jump beside the telescope, and you'll see the spike actually on it, where it shows the vibration, where the telescope can read it and still find itself back where it's supposed to be as it's moving. And we've got the software here. It's called the Sky, which is aptly named because that's basically what's in it. And it's got a map of the entire sky. So stars, planets, galaxies are all mapped out in this piece of software. And this is where I joke with kids that are coming in to see the telescope that it's actually easier to use this telescope than it was to use my own backyard telescope, because you had to set it up every night when you're out under the stars, recalibrate it, align it with Polaris so that it tracks properly. This thing, literally, we turn it on and it's good to go. And then I just point at an object. So right now, let's see, we are pointed here in the sky towards Sagittarius, so toward the southern sky. I'm going to flip it over to the other side, and we are going to point toward the North Star. So there's Polaris over here in Ursa Minor. And all I have to hit is slew. So we go to our telescope tab and the slew button, and the telescope will move itself and reposition to Polaris. Now, normally the dome would also be aligned with the telescope, and it also moves on it. So the advantage to this is that we could be actually at home. I could be sitting at my house, and when we do the virtual Starry Night streams, none of us were even here. We were just running the telescope remotely.
Wow.
But because of the rain, the dome does have a few points where it does leak some water. So I didn't want to rotate the dome too much today, because I don't want to get water inside the telescope. But I will show you a little bit about how it moves, because it is a fun thing. So I'll move it slightly so you can get a sense of what that's like.
Open the darn thing. See if it opens.
Yeah. And that will be the last day that I work at the observatory.
They're getting a little bit of rain out in BC, Bill, I hear.
Oh, no, that's true. Keep the damn thing shut. Sorry.
And then there you go. And then we got sort of this black skirt on the front of it, this sheath on the front of the telescope right now. And that was mainly because over the course of the break, there was some new lighting that was installed on campus, and we found that it was starting to leak into the telescope. The university has been cooperating with us in trying to relocate or re-angle some of those lights. But in the meantime, we've got the shroud over the front to kind of keep it safe. And then, of course, our one favorite addition here, which is the TARDIS from Doctor Who that we have inside. And that's a reminder to those of you who happen to know Doctor Who. It's about time traveling. And we use that to talk to people, because our telescope is essentially, it's a time machine, right? When we're looking through space, we're also looking backward through time. And as we're looking through space, we can image space as well. So on this side of the telescope over here, we have our main astrophotography camera. And
for the nerds in the crowd, what kind of camera is it? Do you know?
So this one is called it's from FLI. The company is called Finger Lakes Instruments, and it's a monochromatic astrophotography camera. So it is enclosed inside of a box where it is actually cooled and chilled down. When you're taking images from space, the light that you're receiving is so faint that it can even be obscured by the heat inside of a camera. And so we actually cooled the sensor down to about minus 20 degrees Celsius. And then around the outside, I'm going to get a little bit higher here so you can see a bit more clearly. This big disc that you see on the side of the camera camera, so this one here, is called a filter wheel. And so what happens is, as the camera is imaging, the filters are swapped out one at a time so that we're only taking a certain color of light at once. And the advantage of that is, in a normal CCD camera, like the one you have in your phone, it might say that it's 12 megapixels, but each of those pixels is actually split up between different colors. So you'll have some pixels that are assigned red, some green, and some blue. But in an astrophotography camera, by using the filters, we can use every single pixel for red, every single pixel for green, every single pixel for blue, and then we mix all the colors together afterwards to create a full resolution image. On this side, over at the end of the periscope, as Bill was mentioning, this is where we normally have an eyepiece. And there's a mirror in the back of the telescope. It's basically a 90-degree prism, and it'll flip one way to either send light out through into the periscope, or it will flip light the other way into the primary camera. So we're either using one or the other, and we can have, there's a motor inside that switches it. On the eyepiece, we can also attach a webcam. And so when we do our live virtual streams to the public when we're not here, we'll just put a camera onto the eyepiece. So you're basically kind of getting a same sort of what you would see through the eyepiece experience from the telescope. And that's kind of a little bit of the ins and outs in operation. And then I thought, if we have time, we can actually show you some of the photos that we've taken with the telescope, because I was hoping we'd look through it with the public, but with the clouds.
Probably not going to happen, huh? Yeah. That would be great. Thank you. So that's a pretty interesting setup. It's a pretty typical setup, but having the filter wheel on and stuff is nice on the camera. We did have a question of whether or not you know of any Canadian companies that supply this kind of technology. You've been referencing PlaneWave, and Finger Lakes, I imagine, is from New York. PlaneWave is Los Angeles?
Yes, they are.
Down there. So a lot of the telescope manufacturers are down in that part of California, really because of the defense industry, I would suggest, but a lot of the really big ones are down there in the US. But can you think of any? There's certainly Canadian distributors, but is there anybody up here making stuff? Yeah, I know that's kind of my answer. Yeah, I don't think so, Henry. So that to Henry's question, but the components and the things that go into building the building obviously were thought very much with the site and the site in mind. So optics and telescope technology is a pretty niche market, and I don't think you find it everywhere.
No.
Yeah. All right, Matthew, have you got some photos, some images, or are you going to pull them up somewhere?
Yeah, I'm signing into the observatory control computer right now.
Okay, well,
and then maybe we'll flip over to that feed, and then we can,
while you do that, Bill, is there anything else you want to tell us about this? And have you designed observatories elsewhere, or is it primarily?
I've only designed a couple. I designed the observatory at the University of Maine in Aurora, Maine. Same thing. We used a PlaneWave there as well, but we didn't take the same design approach. We took a different approach. But the one in Aurora, Maine, at the University of Maine, is way larger. It includes a classroom.
Oh, okay.
Yeah. So the 30 students can come and sit in a classroom environment in front of computers, and they can see stuff that's going on. And we had an advantage. There was a huge hydroelectric plant on the site that had a very, very dense base of concrete created for it. So when they built the observatory on top of it, we didn't have to do what we did in Vancouver, which is create this deep pier, because it was so solid that we were able to get the telescope onto a very kind of minor mount, if you will, and get it sitting there. So that was a different experience completely. But this, Christian, my basic experience is planetariums. I've designed over 30 of them in the world. So, but observatories are 2, maybe 3. Yeah, maybe 3.
So if we had a planetarium that we wanted some observing done at, that would be possible. You know how to put them together.
Yes, if you put it in downtown Toronto, it'll be a little bit of a challenge, but
that's okay. I can see stuff from my backyard. All right, Matthew, I think we'll wrap up with a few beautiful images from the Trottier telescope. If anybody has questions for Matthew or for Bill or for me, it's probably time to put them in the comments, because we're getting past 10 o'clock in Toronto time. I know you guys out in the West Coast are just getting going, but we're winding down. So we're going to just take a couple more minutes to have a look here. All right, what you got?
First of all, can everyone hear me okay?
Yep.
Yes, we
Great,
can hear you fine.
My headset microphone has been a bit scratchy. It's good. I'm so excited to get to be in here too, because it's the one part that's heated in the observatory. So thank you.
The warm room. Yeah.
The warm room. Okay, let me share my screen with you.
Oh, we were having lots of fun with this earlier, but no, that's okay.
Oh, that's Tim.
Look
I know.
at that.
Here we go. Okay.
There we go.
So we'll go to the desktop, and I've got some of the pictures that I was going to show.
Okay.
Okay, so a little bit different for this one. One of the other things that we've imaged has been moving objects. So we had Comet 41P come through the solar system in August a couple years ago. So these are individual subframes of the comet as it was passing through the solar system. And we wanted to see if we could image it. And at the time, what had happened, there was a package of software that had to be installed on the control software to track a moving object that was moving relative to the sky. And we didn't have that installed yet. So what had happened is the telescope is moving, but it's tracking the background stars rather than the telescope itself. And so this is the telescope's still tracking, but the comet is moving relative to those stars, so you can see it actually moving. And then the strips that you appear on the bottom and top are probably satellites that have moved through the image. So what we tried to do, I took all the images and I used the software to stack all of them to the moving comet just to see what would happen. And it actually created a really cool effect. So this is the final image. And I felt like it gave a sense of motion for the comet. The comet is about the size of a mountain. It's about 1 kilometer across.
Wow.
And so here is the image with this kind of streaky stars in the background. So we have taken stationary, deep space objects, but we've also tried to take pictures of moving objects as too. So this was us trying to track a comet through the solar system.
Matthew, Julie wants to know what the aperture is of the telescope. What size is it?
So the telescope is 70 centimeters is the primary mirror. Yes, it is quite large. I think it's one of the bigger ones in the Lower Mainland. So so 70 centimeters.
It's probably one of the bigger ones in all of Canada, to be honest.
I would imagine so. Yeah.
Pretty big.
It is actually.
Yeah.
Ooh, looks like that's a nice one. This is an object that's up in the sky probably right now.
Yeah, it's getting there. One of my favorite things in the sky, the Orion Nebula, of course, in the constellation of Orion. And Orion is one of those wintertime constellations. So we're starting to see it return to evening skies again. So this is an exposure of about 20 minutes. So not super long because it is very bright. And like we were saying, with the filter wheel rotating, you're taking individual frames that are then layered together. So this is made from about 650 1-second exposures that are running through red, green, and blue to then make the final image. And the center of the nebula here is a bright star cluster called the trapezium cluster. And so if you could see the nebula in 3 dimensions, it would actually be concave toward the center with those stars sitting out toward the end. And we mentioned when we were walking along the plinth that hydrogen, one of the primary colors that hydrogen glows in when it's emitting light, is in red. And so nebulae like these, hydrogen is glowing red as it's being excited by the stars. But some of the starlight is actually blue from the brightest stars, so that they tend to mix together. So the star-forming regions in space are this magenta color. I love that. You can actually see this nebula with the naked eye. So when you're looking at the stars of Orion, there's the 3 stars of Orion's belt, and then just below the 3 stars of Orion's belt, one of those stars is actually the light of this entire nebula. So that's one of the other images from the planet.
So Pride wants to know who took that picture.
So this is my photo. I took this.
There you go.
Yeah, and so from the observatory, and that was over an evening of letting the computer do its thing, taking its pictures. Most of the software that we're using here at the planetarium to then do the post-processing on images is with a software called PixInsight. And so it'll layer the images together, and then we can also boost up the resolution. So I have a kind of a comparison before or after from the initial point of processing to later on. Can't quite make it out here, probably through the stream, but the picture on the right is like an earlier version of the image. The one on the left, you can see a lot more definition in the clouds.
Yeah, the
and
stars
nebular gas.
are also sharper. Yeah.
Yeah, so it's about almost twice as much resolution from beginning to end that the computer is able to pick out. And it's mainly because between the images that are being taken, the software starts to pick out the impact made by the atmosphere in the image, and it's able to remove that from the pictures, which is pretty cool. Sorry, go ahead.
I just looked back, and Haley wanted to know where the moon bench came from.
That I don't know. I don't actually know, because it was added afterwards, and I'm not actually sure where the moon bench came from afterwards. But that is a good question. Bill, have any idea? I don't know about that one.
No, I don't. I'm sorry.
Yeah. No, that is a good question. That's one I'll have to look up for you afterwards.
But I really like it.
Yeah, it's really nice. Yeah,
very
it definitely
nice.
is.
I just wanted to mention that Tom noted the Canadian optical system Saravolo in Ottawa. Yeah, that's they're a force of nature, and many of us in the Astronomical Society know them, and they do produce components for, I think, cameras, and imaging stuff, and they're great. Anyway, sorry, just wanted to mention that.
Yeah.
All right, what you got?
One more I'll show before I can, and then, so this is an image of the Andromeda Galaxy. So opposite to what we were talking about with Orion, which is hundreds of very short exposures, because the Orion is very bright comparatively to a distant galaxy. So this of Andromeda is about 65 5-minute long exposures each. And the fact that you could do a 5-minute long single exposure and still have the images be sharp and not blurry really speaks to the tracking quality of the telescope. And so this is, Andromeda is enormous. In the field of view of our telescope, you'd have to do a mosaic of almost 6 pictures to get the whole thing in all at once. And I was going to do that, but then Professor Howard Trottier, who was lead at the observatory at the time, told me I'd be crazy to try to do it. So he's like, just pick one angle and just do that. So that's what I did. So these are the inner spiral arms of the galaxy. Over here, you have some of these magenta clouds, which are similar star forming regions as to the Orion Nebula in our own galaxy. So we can actually see them all the way across space, forming in the spiral arms of the Orion or of the Andromeda Galaxy. The core of the galaxy is here, and we have the spiral arms. Now, what was happened, because Bill mentioned that the telescope was designed to do both outreach, but also some research. And so in this image, it was serendipitous that one of the stars that was captured, and I've zoomed in on it in this version here, that one star with the little circle around it is a variable star called M31V1. So the Andromeda Galaxy is also known as Messier 31, and this is variable star 1 in that galaxy. And there is a woman named Henrietta Swan Leavitt who found a way to measure distances across space using these types of variable stars. And that research was followed up on by Edwin Hubble, whom the Hubble Space Telescope is named after. And Hubble, using this star, this one star, and a few other stars in the spiral arms of the galaxy, used that star to make the distance calculation to Andromeda for the first time. And that's what led us on to understanding that we were not the only galaxy in the universe, that the Milky Way was not the whole universe, and that Andromeda was in fact a whole other galaxy. And then, of course, since that time, we're pretty sure there's probably more than 2 trillion galaxies in the observable universe. But it was this one little star in Andromeda that unlocked that big universe for us. And for me, that was quite meaningful, because first of all, I didn't know that piece of space history until Howard had explained it to me. But Andromeda was also the thing that opened up space to me, because it was my grandfather who showed me the Andromeda Galaxy in the sky for the first time, and was the person who got me into astronomy. So he now has this picture of the Andromeda Galaxy in his office. So,
did you run out of socks? What happened?
Oh, I don't wear matching socks on purpose, because it takes too much time to match them, and
Absolutely.
I just find life is more interesting that way. I also heard Einstein didn't match his socks. So
it's what Zoom's for, right? We don't have to match our socks.
We don't have to match socks.
That's a really meaningful picture, and just the story of the Andromeda and learning our place in the universe. It kind of comes back to a theme of, we're slowly Earthlings slowly became not at the center of their universe anymore.
That's
And
right.
every new discovery, our universe got bigger and bigger and bigger.
Bigger and
And
bigger.
there's actually quite a lot of tie-in also to the history of astronomy in Canada. In my side of the world, we have Helen Sawyer Hogg, who used to investigate globular clusters. Another famous woman. I love it that all of the astronomers we've talked about tonight are women. It's great. There's a lot of us. Yes.
Oh, yeah, and foundational to our understanding
Absolutely.
of like massive things in the universe.
They organized all the guys into doing stuff. Yeah,
That's yes,
how
they
it works.
did. Yeah. One other fun picture I'll show quickly. This is what happens when you get photobombed by the International Space Station. So that happened once when it flew through one of our exposures, and it's very, very bright.
It is. Yeah.
And then this isn't from the observatory, but I took up my own personal telescope, and I figured, but since it's the moon is a theme for tonight,
perfect.
This is my favorite moon photo that I took. So we won't be seeing the moon tonight from Vancouver, unfortunately, but I figured I'd at least leave off on an image of it. So there we go. And,
that's absolutely fantastic. Thank you so much, Matthew. There's just a great tour. Bill, a wonderful insight into the challenges that you were facing there. And we certainly hope that you'll be facing some similar challenges in Toronto in the not too near future.
Yep.
For everybody who's joined us tonight, I just want to have you join me in thanking the speakers. Randy, I think, went off and got some dessert or something. He's not in the stream anymore, but maybe he's setting his telescope up. I don't know. We do want to remind you that the Trottier Observatory is a going concern with their wonderful Starry Night tours. That's what you call them?
Yeah, so we have, if you're in the area, you can always come out. We do host Starry Nights again in person. We weren't doing them in person for a while, but we are again in person up on Burnaby Mountain on Fridays. And so the best way to do that is to check out our social media. So there's a Twitter handle for the Trottier Observatory. As well, we have a Facebook page, so you can always check out the Trottier Observatory Facebook page, or just check out the website. If you Google Trottier Observatory, you'll find it there. And we also will sometimes be doing the virtual stream. So if you're not in the area as well, I don't know why my focus is all done here, but if you're not in the area, you can always tie into, or we should be doing the virtual streams at least once a month. We're going to try to still be doing them, so you can always tie into us online as well.
Excellent. That's great. And definitely want to do that. I want to see this thing in action for sure.
Yes.
Also for us, you heard me earlier talking about Space Place. Just a final thing about how to help on our campaign. We are taking donations to help with our awareness campaign and eventually with the actual business of getting this thing done. We do have members. If you already are a member and are online, you can renew. Please let us know if you would need some help with that. And if you have any inquiries, you can email us. Our email and contact information is on our website, spaceplacecanada.ca. And if you've seen any of our streams before, you know that we actually have some swag that we can send you. If you donate, we have Space Place masks, face masks, which we hope we're not going to need for too much longer. And we also have some music from the planetarium in Toronto, the old McLaughlin Planetarium, for download. And it's a wonderful sort of memory, if you remember that, as well as some books by our very own Bob McDonald, who is actually closer to the Trottier Observatory. I believe he lives in Victoria. And he's got his wonderful book about the universe, which I've read and my kids have read and they love. So if you have any interest in any of that, please do get in touch with us. And with that, I would like to thank you all for sticking it out. 2 hours of astronomy on a cloudy, rainy night. It's fantastic. I hope that you get some sleep and maybe get up and watch that eclipse through a live stream or in person. And we do hope to see you all again very soon. Thanks very much. Good night.
Thanks, everybody.
Good night.
Bye.